In the last section, we defined differential entropy. In this section, we define joint differential entropy, conditional differential entropy, and mutual information. Definition 10.17 says that the joint differential entropy Hx of a random vector x of dimension n with joint PDF f of x is defined as minus integrating fx log fx dx, where the integral is over the support of fx. As usual, this can be written as minus expectation of log of f of the random vector x. As a corollary of this definition, if x1, x2 up to xn are mutually independent, then the entropy of the random vector x is equal to the summation of the entropy of the individual random variables. With definition 10.17, we have a vector generalization of the translation property, which says that by translating the random vector x by a constant vector c, the differential entropy does not change. We can also prove the scaling property for a linear transformation of the random vector x, namely A times x, where A is a fixed n by n matrix. Specifically, the differential entropy of A times x is equal to the differential entropy of x plus log of the absolute value of the determinant of A. We leave the proof of these theorems as an exercise. Theorem 10.20 gives the formula for the differential entropy of a multivariate Gaussian distribution. Let the random vector x be jointly Gaussian with mean mu and covariance matrix K. Then the differential entropy of x is equal to 1/2 times log of 2 pi e to the power n times the determinant of K. Here is the proof. Let K be diagonalizable as Q times lambda times Q transpose, where Q is an orthogonal matrix and lambda is a diagonal matrix. Write x equals Q times y, where the random variables in the vector y are uncorrelated with variance yi equals lambda I, and lambda I is the ith diagonal element of the matrix lambda. Since x is jointly Gaussian and y is a linear transformation of x, y is also jointly Gaussian. For a Gaussian vector, if the random variables are uncorrelated, then they are mutually independent. Therefore, the random variables in y are mutually independent. Now consider entropy of x equals entropy of Q times y. By the scaling property, the entropy of Q times y is equal to the entropy of y plus log of the absolute value of the determinant of Q. We have seen earlier in this chapter that the determinant of Q is equal to plus or minus 1, and hence log of the absolute value of the determinant of Q is equal to log 1, which is equal to 0. Now, since the random variables in y are mutually independent, the entropy of y is equal to summation entropy of yi, I equals 1 up to n. Since yi is Gaussian with variance equal to lambda I, the entropy of yi is equal to 1/2 log of 2 pi e times lambda I. Now we take the 1/2 outside the summation and write the summation of the logarithm as the logarithm of the product. Specifically, there are n occurrences of 2 pi e, and we have the product of lambda I equals 1 up to n. Now the product of lambda I equals 1 up to n, is equal to the determinant of the matrix lambda, because lambda is a diagonal matrix. We claim that the determinant of lambda is equal to the determinant of K, and this is seen as follows. Recall that K is diagonalized as Q times lambda times Q transpose. So the determinant of K is equal to the determinant of Q times the determinant of lambda times the determinant of Q transpose. Now Q and Q transpose have the same determinant, and so we have the square of the determinant of Q times the determinant of lambda. Recall that the determinant of Q is equal to plus or minus 1, and so its square is equal to 1, and therefore we have the determinant of K is equal to the determinant of lambda. This completes the proof of the theorem. We now introduce the model of a channel with discrete output. We say that the random variable y is related to the random variable x through a conditional distribution py given x, which is defined for all x if y is obtained by passing through x through the channel py given x. Here, the distribution of x is general, but the distribution of y is discrete. Likewise, we introduce the model of a channel with continuous output. We say that the random variable y is related to the random variable x through a conditional PDF fy given x, which is defined for all x if y is obtained by passing through x through the channel fy given x. Here, the distribution of x is general, and the distribution of y is continuous. With this setup, we can now define the conditional differential entropy. Let x and y be jointly distributed random variables, where y is continuous and is related to x through a conditional PDF fy given x, which is defined for all x. This is illustrated in the figure. The conditional differential entropy of y, given x equals a particular small x, is defined as hy given x equals x equals minus integrating fy given x log fy given x dy over the support of y for that particular x. And the conditional differential entropy of the random variable y given the random variable x is defined as hy given x equals minus integrating hy given x equal small x dfx, where the integration is over the support of x. And this can be written as minus expectation of log of f of random variable y given random variable x. For those of you who are not familiar with measure theory, you can by and large think of dfx as fx dx, while keeping in mind that x can have a general distribution. Proposition 10.24 says that if y is related to x through a conditional PDF fy given x, then the density function of y exists and is given by integrating fy given x dfx. This proposition says that the PDF of y exists regardless of the distribution of x. The next proposition is the obvious vector generalization. We now prove proposition 10.24. First of all, the marginal CDF fy of y is equal to the joint CDF fxy evaluated at infinity and y. And this is equal to the integral of fy given x v given x dv, where v is the dummy variable for y, and v is from minus infinity to y, and then integrate with respect to dfx of x, where x is from minus infinity to infinity. We now show that fy given x of v given x is absolutely integrable. Consider the above integral with fy given x replaced by the absolute value of fy given x. Since fy given x is non-negative, the absolute sign can be removed. And as we have seen, this is equal to the joint CDF fxy evaluated at infinity and y. And this is equal to the marginal CDF fy of y, which is less than or equal to 1. That is, the integral is finite. And therefore, fy given x, v given x is absolutely integrable. Now, with this formula for the marginal CDF of y and the fact that fy given x is absolutely integrable, by Fubini's theorem, the order of integration in the marginal CDF fy of y can be exchanged, and so fy of y is equal to integrating the square bracket with respect to dv for v from minus infinity to y. Then the marginal density function of y, fy of y, can be obtained by differentiating the marginal CDF fy of y with respect to y. Now we denote the square bracket by g of v. And so this is equal to d by dy, integrating minus infinity to y gv dv. And by the fundamental theorem of calculus, this is equal to g of y. That is, the dummy variable v in g is now replaced by y. And g of y is obtained from the square bracket above, with the dummy variable v replaced by the variable y. That is, integrating fy given x, y given x, dfx of x for x from minus infinity to infinity. This proves the proposition. We are now ready to define the mutual information. Let y be a continuous random variable obtained by passing a general random variable x through the channel fy given x. The mutual information between x and y is defined as expectation of log of fy given x divided by fy, which can be expressed in integral form as displayed. Again, dfx can be thought of as fx dx. When both x and y are continuous and the joint PDF fxy exists, ixy can be written as expectation of log of fxy divided by fx times fy. With this definition, the mutual information is defined when one random variable is general and the other is continuous. In Chapter 2, the mutual information is defined when both random variables are discrete. Thus, the mutual information is defined when each of the random variables is either discrete or continuous. That is, the two random variables can be discrete and discrete, discrete and continuous, or continuous and continuous. We are now ready to define conditional mutual information. Let y be a continuous random variable obtained by passing through two random variables x and t, both general, through the channel fy given x, t. Then the mutual information between x and y given t is defined as the expectation of log of fy given x and t divided by fy given t. In integral form, this is the integral of ixy conditioning on a particular t, the f of t, over all t in the support of t, where ixy conditioning on a particular t is defined in exactly the same way as the mutual information between x and y, except that everything is now conditioned on a particular t.